Today we're going to talk about maximizing condensing boiler performance. As a topic, well, one of the things I do for the company is I do travel around talking with engineers, doing presentations. And for the presentation that I give, this is probably actually, this or a version of this, tends to be one of the more popular topics with engineers when it comes to the whole condensing boiler arena. So a couple of slides here. Material is copyrighted. If you do want a copy of it, just either in the forms you fill at the end or send Miranda an email asking for a copy of it as a PDF. We can get that to you. The program is accredited for continuing education, and here's our accreditation provider, so we have that information. And now on to the learning objectives. So, from the aspect of the conversation, it's all about maximizing condensing boiler performance. So completion of this session, you will be able to describe the effects of return water temperature on condensing boiler performance, explain how outdoor reset control aids in maximizing condensing boiler performance, discuss the role differential temperature plays in efficiency, and then finally describe how the various piping arrangements components affect the system performance. And when we look at condensing boiler performance and maximizing it, you'll find everybody has a hand in it, from us as the manufacturer to the specifying engineer to the installing contractor to whoever's doing the startup and the commissioning. You know, a successful project, everybody thinks about it and does what they need to do along the way, and that's really the bulk of our discussion. Now, since this presentation is, think of it as the third in a series of three that I've done over the past couple of months. For those that haven't attended the first couple, I'm going to cover a couple of quick slides to bring you up to speed on the other two topics because of the way they all interrelate together. Now, the first one was really about condensing theory. And when we talk about condensing versus non-condensing boilers, it's really the real difference between the two of them, other than the construction to be able to take the condensate, really is about how and what part of the energy that's released during the combustion process that the boiler is able to tap or extract from. Now, the energy really comes down to two sources: sensible heat and latent heat. Sensible heat is the heat that a non-condensing boiler works off of, and it's also heat that a condensing boiler works off of as well. It's called sensible heat. It's a heat you can feel. So I have combustion in my combustion chamber. My combustion gases has a certain temperature. That temperature represents sensible heat. Now, as I pass my combustion gases through the heat exchanger, I extract the sensible heat, and how I see this is a drop. My combustion temperature is much higher than the temperature that I see at the flue of the boiler. This makes up about 90% of the energy. That's why when we look at condensing and non-condensing boilers, they typically top out at about 87, maybe 87.5% efficiency. The rest of the energy, this latent heat, is heat that they can't touch by simply changing the temperature. Now, when we talk about latent heat's all about one of our products of combustion, water vapor. Now, when that water vapor forms, that water vapor has the latent heat of vaporization in it. And in a condensing boiler, what we're actually trying to do is we're trying to change the phase, change it from a vapor to a liquid. And as we change from a vapor to a liquid, energy is released. And what we're trying to do is have this happen in the heat exchanger of the boiler and extract that energy. So we change, so we'll reduce the temperature, we'll get to the dew point. Once we hit the dew point, then we start to see that phase change, and when that phase change happens, that's where we start to pick up this energy. And again, when I look at a condensing boiler, it's not just about the boiler condensing that drives the efficiency, it's a bunch of stuff. So what happens is I do get heat from the condensate, from that phase change of my condensate that's now being gathered by the boiler. Additionally, my stack losses are much lower as well. A non-condensing boiler, we're talking about stack temperatures 300, 350, 450, 500 degrees. When I do a condensing boiler, my stack temperature or my flue temperature is typically within about 20 to 27 degrees of the return water temperature. So round numbers, if my return water is coming back at 120 degrees, my stack temperature might be 145 to 147. So my flue gas losses, the sensible heat losses, are lower. And then all of my other losses become lower as well because I'm doing a modulating burner, I'm modulating the water temperature, I'm getting the water temperature down, and typically the boiler is better insulated. I start to add all of this together, and that's how I get the efficiency away from, let's call it about 87, 86, maybe 87% efficient, into somewhere in the 90% range. Okay. Now, in order to get the boiler to condense, I have to get the return water temperatures down below the flue gas dew point. And that dew point, it's not a set temperature. So, from a definition standpoint, it's the temperature which a parcel of gas or air must be cooled in order for the water vapor to condense to water. So it's that temperature that when I look at my flue gas temperatures, and I'm really looking at return water temperatures, that's the thing I can control. I get that water temperature down below this dew point, the boiler will condense. Now, the thing with the flue gas dew point, it's not a set number. It's actually tied to the combustion process. So in the class about combustion, we talked quite a bit about the combustion process itself, but trying to keep it down to, say, one slide about combustion. Okay. If I want to control my losses and control my dew point, I should have combustion with minimal excess air. Now, one of the things that we use to set up and monitor the combustion process is we will measure the amount of carbon dioxide as a percentage of my flue gases. And ideally, I want that CO2 number to be somewhere between about 8.5 to 10% of my flue products. I do this, my dew point for my combustion products is going to be somewhere probably about 127 to maybe 130, 131 degrees Fahrenheit. So this is how I control that dew point to give the boiler the best chance to condense. I also want a fully modulating input. I don't want the boiler to be step fired, so I can match the output of the boiler with the load of the system. And then the other thing is I also want precise calibration through the entire firing range. What that really means is when I look at the CO2 or the burner setup, I want the high fire burner setup and the low fire burner setup to be consistent. Consistent means probably within about 0.5% as measured by CO2 between high fire and low fire. By doing this, my losses stay consistent from high fire to low fire. Also, my dew point stays consistent from high fire to low fire. So the burner now is set up to drive the best efficiency that the boiler and system are set up to drive. And again, that's trying to keep the combustion discussion down to a minimal amount of slides and discussion. But again, from an aspect of what we're trying to do is we're trying to get that boiler to condense. From a burner setup standpoint, we set the burner up so that the burner is in the flame and the combustion products are in the best condition to get the boiler to condense. And now it's a discussion of how do we set up everything else to drive that process forward. So it becomes a discussion of what influences the rate of condensation. I say part 2 because part 1 is combustion. Now we look at part 2, and what we're really going to discuss today, it's really mainly a discussion about return water temperature. How do I get the return water temperature going back to the boiler as low as possible? And from a condensing boiler standpoint, that's really the focus. The supply water temperature is really secondary. It's really the return water that we have to focus on. Okay. And as I said, the discussion becomes how low can I go with that return water temperature? Now, one of the things that we run across on a regular, if not a daily basis, is applications that on the surface don't look like a good fit for condensing boilers. So particularly I'm doing an existing building, or maybe it's a project that the heat emitter, somebody thinks the heat emitter needs a higher water temperature. So we're in an application that supply water goes out at 180, returns at 160. Yeah. When I typically talk about dew points for condensing boilers, typically I'm thinking the dew point is probably going to be somewhere in that range close to 130 degrees Fahrenheit. So this return water temperature is dramatically above the dew point. The boiler doesn't condense. I don't drive good efficiency. So with condensing boilers, it's all about how do I get those water temperatures down. And when I do a high temperature, particularly a retrofit boiler, my question always is, am I tied to those numbers? And a lot of times the answer will be yes, but they should say yes with a little asterisk next to it. I'm tied to these numbers on the design day. That's when my heat emitters have to put out their design amount of energy. So when we start to look at applications, the question is, well, can I vary the water temperature over the time period? Because as I vary the water temperature, the efficiency changes. So this is a generic chart looking at boiler efficiency. You could probably find it on the internet. You can also find it in the ASHRAE manual. The bottom scale is on return water temperature. The vertical scale is boiler efficiency. So I can look at, in a generic format, any return water and come up with a round figure of where the efficiency should be. So for instance, if I look at that existing building with the water coming back at 160 degrees, at 160 degrees, my efficiency is 86 to 87%. So I'm probably in the neighborhood with some of these near condensing boilers. If I'm doing retrofit work, that's probably better than what was installed in the building, but not as good as it can be. Because if I get the water temperature down, let's say I get it down to 120 degrees. At 120 degrees, I'm now below the dew point. And at 120 degree return water temperature, I'm looking at about 90% efficiency, much better. If I can get that return water temperature down to 100 degrees, that brings me up to about 94% efficiency. So really the key is let's drive the water temperature down, and as I drive it down, the efficiency goes up. So what does that mean for my existing building with the high temperature system that's going to run at 180 going out, 160 coming back? You know, something with fin tube baseboard or some sort of convector that's also of a fin tube type arrangement. Or maybe I have some air fan coil units that are sized at 180 degrees. Now, the thing is with most heat emitters, most of these heat emitters, as I change the water temperature to the heat emitter, the output of the heat emitter drops off, and in most cases, fairly close to a linear relationship. So what I can do when I'm looking at water temperatures, if I can do something to change that water temperature, I can affect the equation. The real thing is, you know, if I can measure the outside temperature and vary the boiler water temperature based on that outside temperature, I can start to drive that water temperature down. Because frankly, when I look at design water temperatures are there for the design day. That's when the heat emitter has to put out the right amount of heat to balance the heat loss of the building. As the outside temperature drops, the need for heat drops as well. So I can modulate, I can change the water temperature, which changes the amount of heat going into the building, which will balance with the amount of heat leaving the building. So we'll do an outdoor reset curve. So we'll do an outdoor reset system with an outdoor reset control. We'll measure the outside temperature, and then we will vary the water temperature based on that change in the relationship through this outdoor reset curve. Now the curve that we show here is looking to achieve about 180 degree water on a 0 degree day. Okay. Now the existing boiler in that building, it was running at 180 degrees because that's what it was set up to do off of its aquastat. But here off of outdoor reset, on a 0 degree day, I need 180 degree water. But for instance, on a 32 degree day, I need about 133, 135 degree water to change the amount of heat being emitted by the heat emitter to balance with the building. And if this is the right curve for that heat emitter building combination, the temperature should stay consistent within the building itself. Yeah. On a 50 degree day, my water temperature is now about 100 degrees. So what I'm doing is I'm balancing the heat load of the building, the heat input with the heat load of the building. But what I'm also doing is I'm dropping the water temperature. And as I drop the water temperature, my condensing boiler can run more efficiently. Now, because of the fact that we always talk about condensing boilers on the basis of return water, let's shift over to a chart that has return water on there. Additionally, on here, I also have some ASHRAE weather data. This happens to be for Boston, Massachusetts. So if I was designing for Boston and my target was for 99.8% coverage, I would design around a 0-degree day. So my design conditions here are 180-degree water at a 0-degree day for that kind of coverage. Now the green line that you see here going between that convergence of those 2 points and the 68 on the lower left-hand corner, the green one's my supply. Now, because of the fact that we are talking about a condensing boiler, I need return water. That's this purple line that just is flashing. So that's my return water. That's where I look at when I'm thinking about my efficiency. Now I have a couple of yellow lines. One's yellow horizontal. That represents my dew point of 130 degrees. Where the yellow line crossed the purple, I've put a vertical line that just turned to a kind of an olive green color. That tells me that this is the crossover point from condensing to non-condensing. And based on this information, this is happening when the outside temperature is about 19 degrees Fahrenheit. So when the temperature is above 19 degrees, the return water temperature is below the dew point and the boiler condenses. When it's below 19 degrees, the boiler is running in a non-condensing mode. But looking at this data, a lot of times when we do outdoor reset with high temperature installations, the discussion is, I do outdoor reset because I'm going to pick something up in the shoulder season. If I can run off of this curve, I don't just pick it up in the shoulder seasons, I pick it up for the bulk of the heating season. You know, greater than 90% of that season, the boiler's running in a condensing mode. Let's put some actual efficiencies to some of these numbers. So if you look at the 28-degree day, on a 28-degree day, if I go out to the vertical axis, on a 28-degree day, my return water temperature is about 120 degrees. This point represents about 88% of the heating season. If I convert that to an efficiency, the boiler is about 90% efficient. So 90% efficient for about 88% of the heating season. To me, that's a lot more than the shoulder seasons. Let's add another point in there. 41 degrees, on a 41-degree day, the return water is about 100 degrees. That represents about 94% efficient. And that for that 94% efficiency, that's looking at about 51% of the heating season. So if I'm doing outdoor reset and I choose my curve carefully, particularly one that there's no minimum temperature associated with it, I can easily drive my seasonal efficiencies beyond the 90% number. You know, with these kind of numbers, I'm probably pushing 92, maybe 93% seasonal efficiency, even though on the design day, I am not going to be condensing. Now let's take a look at how the reset usually shows up in projects. So that little table in the corner, I see that on a lot of projects, usually somewhere in the details or the operational part of the package or the schedule for any kind of boiler plant. And they usually specify 2 different points for the heating curve. You know, something usually on the design day and then somewhere in the 60, maybe 65, 68-degree point as well. So if I had some sort of limitation, for instance, on a 60-degree day, I'm going to say my boiler temperature is 130. That 130 is probably based on either the limitations of a heat emitter or from the limitation of a heat emitter, possibly it's an air-based system that because of the coils being utilized, if I go any lower in the temperature, you'll have a cold blow coming out of the registers. So that becomes the lowest the water temperature can be. And then we specify the high side. On a 0-degree day, it's 180-degree water. Okay. So 2 dotted lines there. There's my minimum water temperature based on heat emitter, which is my 130. The high line is my 180 degrees based on design conditions. In most cases, when I give those 2 points, that's what I end up with my heating curve. It either becomes a linear straight curve, or if the boiler control has a slope and shift setting, I'll adjust the slope and the shift to bring the heating curve there. Now, since efficiency is not based on supply water, it's return water, this lighter purple colored curve, that represents my return water. I have a fairly even spacing. I'm going to assume I'm running off of a VFD, then I'm changing the flow rate. But what you see here is that minimum water temperature at 130. We're also going to call that my dew point, since I expect the dew point to be somewhere around there. All of a sudden, that area right there, that part of the heating curve, represents when the boiler is actually running in the condensing mode, about 24% of the heating season. And from an efficiency standpoint, if I go to the far left-hand side, I'm sitting at probably about 112 degrees Fahrenheit, which is probably somewhere a little bit more than 92% efficient, maybe 92 in that range. So the highest the efficiency becomes is 92%, and it's for a small fraction of the heating season. All of a sudden, this application, it becomes very difficult to budge above the 90% number for the seasonal efficiency of the boiler. Now, with the heat emitter, this purple curve really is not a good representation of its response to a change in water temperature. Okay. If I do the blue line that's going to populate in a minute, if I do that combination, the curved part of the blue line from 0 degree day at 180 down to on a 41 degree day at 130, that actually represents a better response to match the output of the heat emitter to the load of the building. And it also allows me to get the return water temperatures, my water temperatures down quicker for an efficiency standpoint. Now, when that heating curve converges with my minimum water temperature, I flatline from that point forward. And I'll have good performance from a heat emission standpoint from my heat emitters. But look at what this does to my return water temperatures. All of a sudden, this yellow line now comes into play as my return water temperatures. So rather than spending 24% of the heating season in the condensing mode, I'm probably closer to about 75% of the heating season in the condensing mode. And rather than spending a very short period of time at 92% efficiency, I'm now spending 51% of the season in the 92% efficiency range. My performance improves dramatically by doing this. Okay. Now, what does this mean from a programming standpoint? Rather than just programming based on a reset schedule as you see above, it becomes a two-part schedule. I still specify my 2 points, but rather than doing 0 and 180 and 60 and 130, it becomes 0 and 180 and 41 and 130. And then the other caveat is that the water temperature is maintained at 130 between 41 degrees and 68 degrees, or whatever that number happens to be. But it's a way to drive that efficiency. And the thing is, you know, making this small adjustment in the heating curve rather than going with the simple point-to-point can reflect, you know, some really decent gains in the seasonal efficiency of the heating equipment. Let's see, any questions so far? No questions, all right. So the first thing with water temperature is, now, how do we control? And how we control can cover every single project out there. Then it becomes, what water temperatures can the building live with, or what can we design around? And again, for me, it's all about return water temperature. So we're going to look at a series of slides that look at the impact of return water temperature. And for here, we're looking really at that crossover point from condensing to non-condensing. So if I take a high temperature installation, could be fin tube baseboard, could be wall mounted convectors, could be air handlers. And let's say I'm going out there, this happens to be a European standard with a little bit bigger temperature drop. But if the return water temperature is coming back at 158 degrees, let's call that 160 to get fairly close to a US standard. Typically, the crossover from condensing to non-condensing happens somewhere in that 26 6 to 24 degree Fahrenheit range. Okay. Now, if the opportunity exists, whether I'm designing for air handler, I'm designing for heat emitters with a lower return in supply water temperatures, or an existing building has the opportunity to drop the water temperature. For instance, when the building envelope has been improved, as well as the heating plant being upgraded. But if I can drop from 160 down to 140 degrees, that crossover point all of a sudden changed from happening on a 25-degree day to happening on an 11-degree day. I've picked up more of the heating season where the boiler will run in a condensing mode, and every day of that heating system, the boiler is going to run more efficiently. So from a design standpoint, if I can design for a lower water temperature, I can then start to drive efficiency even lower. This is where radiant shines. I do a radiantly heated system. Typically, radiant systems are designed around lower water temperatures. Here, going out at 104, coming back at 86 degrees. This is significantly lower than the dew point for my combustion gases. It being that low, all of a sudden, my efficiencies of 94, 95 plus are achieved throughout the heating season, not just on certain portions of the heating season. So it's about how I control, it's about how I design for my maximum water temperatures. Now, the other thing that I can apply to my water temperatures is not only do I design for a lower maximum, but also let's take a look at my temperature drop in the system. Typically in North America, for years and years, the standard has been a 20-degree drop. I go out at 180, I come back at 160. It's easy to design for, it's easy to calculate flows, it's easy to do all of my calculations. But from an aspect of performance, the question then becomes, can I get to a larger differential temperature or delta T or drop in the system? Let's not do 20, let's do 30 or 35 or 40 or a higher number. By opening those up, I may have to still, for the application, come out at a high temperature, but if I can open up the delta T, I'm bringing down my return water temperature, and the return water temperature is really what matters, okay? In a lot of situations, it may be a little bit of oversizing, or it just may be how I apply. So for instance, here's a table from an air handler manufacturer. It happens to be First Company. I chose this because the chart is really a nice chart to work with. But I can look at an application, exact same air handler, and let's say for that application, I have 50,000 BTUs per hour. Right here in at the 6 gallon per minute block, I can do 50,000 BTUs, 49.6, it's 50 in my book, with 120 degree water and with 6 gallons per minute flow through the heat exchanger, and the fan speed is going to be on high. That achieves that 50,000 BTUs for me. If I look at this number here, there's another 50,000, 50.4. I can achieve that with 140 degree water at 2 gallons a minute at low fan speed. The question though becomes, what's the better combination to achieve if I'm trying to make the boiler condense? On the surface from our previous discussion, you'd look at it and say, oh, immediately 120 going out is lower than 140. The return water must be lower. That becomes the better setup. However, flow rate through the coil plays a big part in this. And if you work the numbers, at 6 GPM with 120 degree water and a fan speed that's high, I see about a 17 degree drop through the coil, giving me a return water temperature of 103. At 140 degrees with 2 gallons a minute and the fan speed of low, I get a 50 degree drop and my return water temperature is 90. So by dropping the flow rate down, verifying that the heat emitter can work under these conditions by charts like this, I can open up the delta T. This one happens to be a 50-degree delta T and get better condensing performance. So it's control, it's design water temperature, it's delta T. I start adding these all together, and the more I can work these together, the lower I can get the return water temperature, and the better the performance can be. Nope, just taking a peek at the questions, and there still are none. So, how else can we affect performance? The next one is not just a design, but this is also a startup and a setup and a commissioning that affect it for the next couple of them. How we size and how we set up pumps have a big effect. It's about velocity, it's about flow right through the heat emitters and how much heat is coming off. So when we start to look at how we size pumps plays a big factor into what kind of delta T. And when I say what kind of delta T, now I'm talking about actual realized delta T, not theoretical. This is the delta T that we're going to design around. Because when we start to look at sizing procedures, there are quick ways and there are in-depth ways of sizing pumps. And typically there's, when we start to use quick ways, there's always going to be some level of thumb rule that is used at some point in the process, which tends to work in the direction of driving the flow rate up. So sizing can play a big factor in there. Luckily, I'm going to drop, I'll come back to that in a couple of minutes. But then also, once I size it, the impeller has to be trimmed, if the impeller is going to be trimmed. And what we're seeing now is a lot of pumps that have the VFDs that are integral to the pump, or an ECM motor. A lot of times the impeller trimming doesn't happen, and it's going to be done electronically to limit the upper end of the flow rate of that pump itself. And of course, in most applications, we're still seeing the multifunctional valves, also referred to as triple duty valve because of some of the other functions. But in addition, excuse me, in a lot of cases, even with the drives, there is a balancing valve associated with the pump to make sure that we're setting the proper flow. Now, how does this show up? Okay. Now, let's say I go through and I do a sizing on the pump. This happens to be a pump curve, and you can see my design point on that middle curve that I can't read the RPM on it, but that's where I should be. Now, as that pump goes in, this pump has a fixed impeller diameter, and so what's going to happen is the flow rate's going to be set by either adding in some sort of balancing device or strictly do it off of the internal control. If the control goes in and it's left in we'll call it, where it can modulate up to the full speed of the control of the pump, what will happen is as I increase the flow rate through the heat emitters, what will happen is the delta T across that heat emitter will shrink, even though it's going to shrink beyond where my design delta T would be. And as the flow rate increases, I lose that delta T. Because the boiler puts out a set water temperature, when I shrink the delta T, how it's seen is the return water temperature starts to creep up or elevate. And as it elevates, I lose efficiency. So when I look at driving efficiency, when I size my pump, the pump should be sized as closely as possible to the conditions that are required for a flow rate for the proper delta T in the system. And on startup, either through the control on the pump or through the balancing valve, the multi-purpose valve that you may see with it, that has to be set as well to ensure that I've brought the flow rate to where it needs to be to support the proper delta T for the return water temperature. Pump rates, pump sizing, pumping rates, and pump setup play a big factor in the success of many of these projects. The other thing that affects flow rate is balancing. Every heat emitter in the building is going to have some form of balancing valve, be it a dynamic or a static balancing valve to set the flow. And this discussion really, I would say, plays more into the static valve, which right now seems to be still a little bit more prevalent in the market than the dynamic valve. But in the setup of the system and the calculation of the pressure drop in each one of the branches or legs, the valve's authority represents a very large portion of that pressure drop. So what happens is if the project goes in and the valves aren't balanced, you know, here's looking at an overlay of a system curves plural and a pump curve. The pump curve is the red curve. But if the balancing valves go in and the balancing valves are left open, you end up with that blue curve to the far right-hand side. And then as the balancing valves are closed, pressure drop is added to the system, and the system curve moves its way up to where its design point is located. But again, if you look at the intersection of the pump curve with the system curves, the unbalanced curve results in a much higher flow rate than the balanced system curve. So one of the things that has to happen is every project has to be properly balanced. You know, I have seen projects that have not performed well, and amazingly enough, all the balancing valves were open, and then once they brought the balancing valves to their proper position, and all of a sudden they started to see much better performance out of the system. So it does play a major factor. Now, let's go back into the world of design. Let's talk about piping. Okay. One of the discussions, particularly when you have a boiler that can be piped either primary, secondary, or primary only, the question always comes up of which way do we want to apply that boiler? And in most cases, my question always is it depends. The primary only has a lot of positives for it, but primary, secondary has some positives as well. So it really is a matter of application-wise. But if everything else is equal and somebody says, excuse me, from an efficiency standpoint, which one will give me the best opportunity to give the best efficiency standpoint, my answer always is the primary only, or you'll also hear it referred to as variable primary, if it's a variable pump on it, that one there will give you, consistent results, whereas primary, secondary, it may not. And let's take a look at the whys. So I'm doing a boiler that's going in primary, secondary. So the boilers will be on their own side of the hydraulic connection or hydraulic isolation with their own pumps. On the other side will be my system. I'm actually going to do a blow up of that connection. So here we're showing it as closely spaced tees. Now for closely spaced tees, general rules of thumb, they should be no more than 4 pipe diameters or a maximum of 12 inches apart. We're trying to generate a point of no pressure drop across it. So hydraulically, the two sides, the system side and the boiler side, are isolated so that their flow rates can operate independently. Okay. Now, from an aspect of what we're discussing today, we're really looking at it really from a return water temperature standpoint. Now, when I do a primary, secondary installation, I can have 3 different balances between the boiler side and the system side. And we're talking about flows. The boiler side flow, or the boiler loop flow, can equal the system loop flow. The boiler loop flow can be greater than the system loop flow, or the boiler loop flow can be less than the system loop flow. Now, where this comes into play and why this is part of the discussion is for the condensing boiler, I want the return water to come back to the boiler as cold as possible. I don't want anything that can elevate that return water temperature. So if you look at this closely spaced tees and the bridge or the crossover pipe between the two set of tees, the water flow between those tees don't follow the water flow of the arrows. That area, the water flow can go in either direction. It can go from top to bottom in the flow that you see, the direction of arrow flow for the system loop. But that flow can also go in the reverse. How does that happen? Well, it's all about that balance. So let's say the boiler loop flow and the system flow are balanced, they're equal. What will happen is the flow that's coming from the system on the return side goes directly into the boiler, and what's coming out of the boiler goes directly up into the heating load. And in that crossover or that balance point, there's no flow movement because there is no imbalance between the two sides. Now, if my system loop flow is greater than my boiler flow, and I'll throw numbers on it to help explain it. Let's say the return water is coming back at 200 GPM. My boiler flow is only 100 GPM. So what will happen is 200 GPM enters, and I'll call it the bottom of these two T's. 100 takes the branch to the boiler, and then the other 100 has to go through the crossover pipe, because 100 gallons is going to come back through here, mix with that 100 to get me back to that 200 number. From a condensing boiler standpoint, that's okay. That's actually good, because in that situation, I'm not elevating the return water temperature. Now, let's say the boiler flow is greater than the system flow. Let's say the boiler flow is 200 GPM, the system flow is only 150 GPM. So 150 is coming up through this pipe, it enters the T, the pump is moving 200 gallons per minute out here, so where's that extra 50 going to come from? Well, when the 200 comes across here, 50 gallons per minute crosses the crossover pipe, and then mixes in with the return water to give me my 200 gallons per minute. Under those conditions, all of a sudden I'm elevating the return water temperature, and potentially I'm losing a little bit of efficiency. So when I start to do a primary secondary connection, that is one of the things that people tend to think about, particularly when the building is running off of VFDs and possibly the boiler may not be, or the boiler may only, or there is very little movement in as far as the boiler water flow. Two boilers with individual pumps, that the flow rate only drops by 50%. Now, one of the things that can be done to help minimize this, potentially it could also eliminate it depending on how many boilers are in the package, is I don't have to run the boiler loop at the same flow rate as my system loop. So if I design the boiler loop for a higher delta T, at a higher delta T, I'm going to have a lower flow rate for the same amount of BTUs per hour being deposited in the water. So if I can increase the delta T, I lower the flow rate on the boiler loop. By lowering the flow rate on the boiler loop, it gives me a better opportunity to ensure that there is no mixing where the system loop drops below that flow rate. Particularly in a multi-boiler situation, I would say this can pretty much cure any possibility of elevating that return water temperature. But it's something that has to be paid attention to if I'm trying to really maximize the boiler's performance when I do primary secondary. That's why when I say, if somebody asks me about it and I say, primary only really is the best application when I'm trying to ensure I get the coldest water back to the boiler. So here's a primary only piping system. Return water comes back, goes directly to the boiler. There's no location there where I can elevate the return water temperature so that I'm driving the boilers for the best efficiency. Again, both of them work. The primary only has less things to consider to get there. I can do it with primary secondary, but I have to consider changing the delta T and the flow rate of the boiler differently than the system side of things. So let's take a look here. No questions and answers. Okay. Now, other ways, other piping strategies to get ourselves so that that boiler will condense. One that we've seen on a number of projects, probably is not done as often as we would like to see it, is really taking a look at how we generate a temperature drop. in most systems, the system is designed that the water goes out to a single heat load. I pull the energy out of the water in that heat emitter, and then it goes back to the boiler to be reheated. Okay. Question always comes up when somebody says, how do I maximize delta T's? My question is, tell me about the heat emitters and water temperatures in your building or the building that you're designing. Can we reuse the water? Can we pull energy out of it from more than once? So rather than just going out and coming back, let's start looking at going out, using, and using again and coming back. So rather than going out to the fan coil units and coming back, let's go out to the fan coils. Let's extract the energy we need at the fan coil and then put that water back in this fluid stream. Then downstream, let's add in another load at a lower temperature. Let's add in another load at a lower water temperature. So let's say that mixing valve is going out to an installation, a part of the building that is going out at 135 and is coming back at 115. You know, my third load, going out at 115, coming back at 80 degrees. So all of a sudden the water goes out there. Any one individual heat emitter may only have a 20, a 25, or a 30 degree delta T, but when I start adding these delta T's together, all of a sudden I can open it up to a 50 or a 60 or an 80. We have seen a number of these projects being done. One that comes up quite often is domestic hot water preheating, where we'll do a bank of indirect water heaters as the water heating source. But then what we'll do is we'll add a plate heat exchanger in there, and we'll use the return water coming back from the coils and the indirects to preheat the incoming domestic water. And let's open that up. But again, in an application where I'm designing from the ground up, a lot of times I can do something like this to open up the delta T's to get the return water temperatures down lower. Other things we take a look at is the use of mixing valves in applications, particularly applications that I may have long periods of time where the boiler has to come to an elevated temperature for a specific load. This happens to show water heating. It could be domestic hot water. It could be a pool or a spa. It could be snow melting. It could be reheat for air conditioning with another load on top of it, underneath it. And the key is when I start to look at a multiple temperature situation without a mixing valve, everything gets the high water temperature that's required for the highest load. So here for domestic hot water, I'm going out at 180. For the water heaters, the building gets 180 as well. And it's coming back from that building not at 140, but probably more like about 160, 165. All of a sudden, this boiler that has the potential to run at a much higher efficiency is running at somewhere around 86% efficient. But I add in a motorized mixing valve running off of its own outdoor reset. I've now separated the heating curve for the building away from the hot water requirements of the boiler. Now all of a sudden, I may run at 180 to generate domestic hot water or heat a pool, but now with the mixing valve, I can get that water temperature down to 120. Goes out at 120, comes back at 110. In most cases, the space heating load has a much higher flow rate than the domestic or the pool heating load. And the return water temperature is usually skewed more towards the heating load side of things. All of a sudden, let's call it 120 degrees, the boiler's running at 90% efficiency. Nice thing about motorized mixing valve packages, they usually have a very short payback period. Let's call it maybe about 2 years for the mixing valve to pay for itself. Very effective at driving boiler efficiency. And it's not just about one mixing valve with high temp. I can also utilize mixing valves to help work internal and external gains in the building in my favor. This requires mixing valve, but it also requires sensors out in the space to monitor to what's happening to the space temperature. So for instance, let's look at a building that has a north and a south riser. Let's put both of the risers on their own individual motorized mixing valve. But now let's put a sensor in each part of the building to monitor the space temperature. South side of the building, it will see the impact of solar gain and external gain on that side of the building. So middle of winter, nice sunny day, north side of the building sees no external or internal gains. It runs off of the heating curve with no influence whatsoever. On the south side of the building, solar gain starts to occur, particularly if the building has a lot of glass area. That sensor in the building starts to see the room temperature or the space temperature starting to go up. It now influences the heating curve to drive the water temperatures down. And as I drive the south riser temperature down, I'm driving the mixed water temperature down, helping with the efficiency of the boiler. So when we start to look at boiler efficiency and we start to look at driving it, we typically take a hard look at mixing valves as part of the package to help drive the overall efficiency. And again, we can make some fairly dramatic gains by adding a mixing valve into the package. Did I see a question pop up? Okay, let's see. You can set the, let me go back up here. The previous. Okay, yeah, okay. So the question is, where here it says 115, the question came up, can you set domestic hot water 115? Typically, that's actually, when it shows domestic hot water there, that's actually domestic hot water preheat is, a lot of times what we'll do there. So yeah, I see the confusion with the 115 and the domestic hot water. It's not actually for the generation of the hot water, it's to preheat the hot water before it gets to the hot water heater. So let's see. So kind of wrap it up and I took the learning objectives and I kind of put them into bullets about the things that we did discuss. So in order to drive the performance of a condensing boiler, once we get beyond the combustion side of things, again, which was from our previous presentation, it's all about lowering the water temperatures. And by lowering the water temperatures, my heat release surfaces, really my heat exchanger gets to the point where I'm below the dew point and lower so I can start getting that boiler to condense more. So it's about lowering the design water temperatures. The lower I go, the better the performance. It's about how I modulate the water temperatures with outdoor reset control. And to me, I want to maximize the strategy. If I have a minimum water temperature, let's see what I can do to stay at that minimum water temperature for the longest time, not for a short period, maybe in the shoulder seasons. If I can, let's look at a higher water temperature drop. Let's design for greater than a 20-degree drop, a 30, a 35, maybe a 40. If I can, let's pipe around that. Let's reuse the water a couple times in a brand new situation. Let's build motorized mixing valves into the project to get that water temperature down. And again, from a design and from a setup standpoint, pumping and balancing are important to driving it from a delivered performance standpoint. Thank you all for coming, and you should be receiving something from Miranda probably within a week or so. Have a great day.